that story later. Okay. Yep. Eutectic. Eutectic comes from the Greek and it means low melting. Okay. E-U-T-E-C-T-I-C. Okay. And that is the eutectic point. That's the lowest melting liquid point. Okay. That little cusp right there. And that comes from the Greek. It means low melting. There's also perictic, which if this thing, instead of going down when I alloy two things together, went up, you'll end up with a perictic phase diagram. And para means the same thing as perimeter. Okay? And basically, perictics tend to segregate in the inside. If you look at a grain as it solidifies, the composition on the inside of the grain and the outside of the grain will be different. And so perictic, it surrounds itself, decorates itself because the alloy segregates and leaves a different composition on the outside than the inside. And so they call it perictic because you end up with this kind of surrounded structure on the microscope. At least that's the best I've ever come up with. Eutectic just means low melting. It comes from the Greek. Yeah. Refractory means high melting. Or actually, refractory officially means heat resistant. So fire brick is a heat resistant material. Aluminum oxide is a heat resistant material. Tungsten, molybdenum, anything melts above 2,000 degrees centigrade is generally considered a refractory metal. Okay, difficult to melt for metals. If you just said difficult to melt, if you're talking about metals, you would consider it refractory. It's hard to get 2,000 degrees centigrade temperatures in a simple furnace, and those are the things that don't melt in furnaces. In fact, in some cases, we make furnace components out of these things. In fact, a common type of furnace, high temperature furnace in the laboratory, is a molybdenum wound furnace. Just take molybdenum wire and you use that as your heating element. And it doesn't melt until 2600 or something centigrade. So you can easily get temperatures up to maybe 1900 degrees centigrade in a furnace, which is hot. I mean, steel melts at 1500 centigrade. So, and you're well above the melting point of nickel and other things at 1900 centigrade. For my doctoral thesis, the problem with molybdenum wound furnaces is you have to protect them from oxidation in the air, because it turns out molybdenum is actually very interesting to see it oxidize in the air. Both molybdenum and tungsten, two of the highest melting metals, form a trioxide, molybdenum oxygen 3 or tungsten oxygen 3. And these oxides are volatile at about 1,000 degrees centigrade. And so I remember once I was visiting one of my former students who was working at a company up in Maine that makes tungsten and molybdenum products. And this is one of the only places in the country where they actually will roll molybdenum plate or sheet. They start out with a big ingot of molybdenum, and it might be 4 inches thick and it might be 3 feet wide. And you have to hot roll the molybdenum or tungsten. And so they pull it out of this furnace at 2,000 degrees centigrade. 2,000 degrees centigrade is basically white hot. And so we're standing up in this room with protective glass and everything, looking down into this rolling area. And there's nobody else in this area, and I'll explain why just so you'll understand in a second. It's all automated. And so they open up the furnace door, and it's all protected by hydrogen and stuff inside the furnace, but they're going to have to roll it in the air. And so they bring out this white hot chunk of molybdenum into this roll, and the rolls are water cooled, not on the outside but internal, so the steel rolls don't melt, from all this rolling. And it comes out on the bed, and the bed automatically starts going back and forth. Well, in the meantime, as soon as it comes out, it starts out white hot, and then you start seeing this kind of looks like a little bit of steam coming off. It's not steam, it's molybdenum trioxide. And within 30 seconds, while this thing's being rolled back and forth, the whole room fills up with white smoke, which is molybdenum trioxide, which is why no one's down there. It's not that it's all that toxic, but nonetheless, you can't see. I mean, after a while, all you can see is this kind of thing glowing kind of red-white through this white smoke. I mean, literally, this is a 2-story high room. It's almost as big as this room, but about 2 stories high with the rolling mill. And just whole room just fills up with smoke, and then they put it back in the furnace, and it's protected by hydrogen, and they bring it out again to roll it again until they finally get it down thinner. Moly plate? Well, moly plate, it's going to get cut up for other little moly things. I mean, molybdenum is going to be used in very high temperature applications. Molybdenum has fairly good thermal diffusivity, so it conducts heat away for a high temperature material very well. The big application for moly sheet at this place was to make masks for semiconductor manufacture. Okay, you have to print the circuit. Okay, so this, if I remember correctly, IBM at that time, this was 15 years ago, was their biggest customer. And they just buy all kinds of molybdenum sheet, and then they would basically etch the molybdenum sheet and make a big circuit, which then get projected down to a small circuit. Okay, so these were masks of some sort to do the photolithography and stuff on circuits. Moly disulfide is a lubricant, the compound molybdenum disulfide, but that's different than molybdenum metal. Molybdenum rod and metal is used in furnaces. It's used a lot in spacecraft because it has a low coefficient of thermal expansion. And one of the problems in spacecraft is on this side of the spacecraft, it's 200 degrees centigrade, and on this side, it's minus 80 centigrade. It's just the way space is. So molybdenum gets used in spacecraft because of its low coefficient of expansion in many cases. It's usually used in small things. They do use moly plate, but usually when they're making some sort of flange, they're going to machine some smaller part out of it. I can't think of an application of big moly plate other than to make smaller parts. Tungsten is essentially made the same way as moly. It's made in that same plant. Now tantalum, which is number 2 common material after tungsten in melting point. Tungsten is like 3,400 centigrade, and tantalum is 3,100 or 3,200 centigrade melting point. Now, I think there may be something like osmium or ruthenium or something that maybe is in between there, but those are precious metals, and there's only a few hundred or a few thousand ounces a year produced in the world of those things, so you don't have to worry about that. In fact, once upon a time, I saw what was supposedly 70% of the world's uridium in one file cabinet at Oak Ridge National Lab when I first graduated. They make these thermoelectric generators for deep space missions, like going by Pluto or something. You got to have something that's going to supply energy. Well, the sun doesn't supply a lot of energy out at Pluto. It goes as R squared, right? It goes down, or the radiant energy from the sun goes down as 1 over R squared. 4 pi R squared is a sphere, right? And you get further out with the radius, you got less sun. So you have to have something to generate electricity for this thing that's going out into deep space. And so they take a piece of plutonium, okay, which is going to, they're not going to go critical, but they're going to have it so it heats up. And so it generates heat. You have to put that plutonium inside something, so they take iridium, which is a platinum group metal. And iridium is similar to platinum, but it melts at 2,400 centigrade or something like that. And they make an iridium sphere and put the plutonium inside it. Now you want this iridium sphere to be ductile and things. First it'll take the heat for a long period of time. You don't want it to corrode. Iridium is very non-corrosive like platinum, but it'll take higher temperatures than platinum. Anyway, because they were making these iridium things, they had something like 70% of the world's iridium all in one file cabinet. They only produce about 100 ounces or something like that of iridium a year. It's a byproduct of platinum production, and they don't produce that much platinum, okay? So it's basically an impurity that comes along with platinum. I made my wife's engagement ring out of platinum iridium alloy, 80% platinum, 20% iridium by electron beam melting it and then machining it, because it's, well, huh? What? I could have killed, yeah? Huh? And I was actually going to make the wedding bands that way too, but the problem was, originally I had to have a crucible to melt this in, so I used some zirconia ceramic, and I didn't have zirconia the right size for the rest of it, and didn't have a bottom plate, so I used graphite, which is high melting, and it turns out I didn't look at the phase diagram. Platinum group metals dissolve a lot of carbon. So the first melt worked just fine, and then I machined it and collected the chips. You don't throw away these chips. Then went to remelt the chips, and I tried for a month. I mean, the wedding date was coming up, and I still wasn't having much success. I kept on getting porosity, and what it was is I was forming carbon monoxide. I finally went to look at the phase diagram. Great. So I ended up quickly designing a new alloy of palladium, gold, silver, copper, aluminum, which I made about 6 wedding bands, figuring that as we aged, we need bigger ones, right? And I could always, so I still have them rough machined in my dresser at home. But it turns out on the 23rd, 24th wedding anniversary, I went out and bought my wife a new engagement, a gold engagement ring, and a new wedding band for myself and stuff. Anyway, rather than going with those, but anyway, my wife always says I should write this down for my grandchildren about how I made the platinum iridium wedding band or engagement ring, because it is somewhat unique. You can go to a platinum foundry and get 10% gold platinum or platinum iridium because you can still work that, but 20% has to be cast. It's too hard, but it actually has about the best corrosion resistance of any material. 20% platinum iridium, or 20% iridium and platinum. But anyway, only a metallurgist would do something like that. But anyway, tantalum, it's interesting. In fact, if you're really interested, I can get you in over here in Newton. Is one of the larger tantalum refractory mills in the world. Tantalum, like I said, is kind of the common refractory metals, is number 2 after tungsten. Tantalum is very ductile and can be worked at room temperature, as can niobium, which is right above it in the periodic table. Tantalum is fairly dense. Tantalum has fantastic corrosion resistance, particularly in salt water. The problem is it's very dense, like tungsten. Not quite as dense as tungsten, but almost. I think tungsten is like 19 times the density of water, and tantalum maybe 16 or 17 times the density of water. So I got a piece of tantalum tubing downstairs, about 6 inches long. I had a student work over there at that plant in the Leaders for Manufacturing program over in Newton. But that little piece of tubing, 6 inches long, is worth about $30, or it's about $60 a foot for a little tubing. But they use it in heat exchangers. They use it in chemical process plants because tantalum has fantastic corrosion resistance. They use tantalum sheet as bone implants, in the skull. If you have a hole in your skull and they have to put a metal plate over it, they probably use tantalum because it's even better than titanium. So they use all kinds of tantalum in medical implant applications. Yeah. Yeah, because you form. In fact, this plant over here, the biggest application of this plant, they have a whole section inside of the plant which makes just tons of tantalum capacitor powder. The tantalum will form a Ta2O3, just like aluminum oxide, Al2O3. You'll form a very, very high dielectric constant tantalum oxide on the tantalum powder. The other thing is, if you process the tantalum powder from the tantalum hexafluoride salt, which is what they do over there, they get these huge bags, like 5,000-pound bag of tantalum hexafluoride salt. Actually, it's not just hexafluoride. It's tantalum. Well, maybe it is. It may be just straight tantalum hexafluoride. But anyway, so they get those from the tantalum mines, and then they reduce it in a very, very complex process to make powders that have very, very, very high specific surface area. So it's basically porous powders. And then they oxidize those to this tantalum oxide. So now you've got a metal powder with a refractory oxide, and you can store lots of charge, more charge on tantalum capacitors than anything else, and they have higher breakdown voltages and other things. Turns out aluminum wound capacitors. I went through a plant in Taiwan where all they're doing is anodize the aluminum. And I showed you how the aluminum anodized gets all this porous structure. For capacitors, you want lots of specific surface area because you're basically storing the charge on the surface. So you want lots of surface area, but you need something conductive underneath. So they use tantalum powders and they use aluminum, anodized aluminum for high capacity capacitors. High capacity capacitors, right? Okay. Anyway, because you can store lots of charge on high surface area, but you need a very, very high breakdown, something that will not allow the current to jump across it. Because let's think about it. If I've got a oxide surface that's 100 nanometers, and I want to put 1,000 volts across that. So let's say I got 1,000 volts, and I've got 100 nanometers, which is 10 to the minus 7 meters, I have 10 to the 10th volts per meter across that little layer. Okay. If I have any free electrons, then I'm basically just going to arc right through there with that kind of field. Okay, that's a field, right? Volts per meter is a measure of electric field strength. That's a very, very strong electric field. Usually, most things will break down at 10 to the 7th. Okay, and you'll just force the electrons to start flowing. So tantalum oxide and aluminum oxide have very, very high dielectric strengths. And so that's actually the largest application of tantalum, so far as that goes. But it's metallic powder. The other tantalum, though, it's interesting. They bring in the tantalum in these ingots that are about 4 inches thick, and they roll it down without any heat treatment or anything. They can roll it down to thin sheet, because tantalum is like copper. You just keep rolling it and rolling it and rolling it without. In fact, copper actually has to be annealed more often. But tantalum and niobium are that way. Not getting to today's topic, but that's okay. For my doctoral thesis, I had to make niobium superconducting wire. And so I would take niobium tubes and put some aluminum in them, because I wanted to form the niobium aluminum intermetallic by a chemical reaction. So I'd take these tubes of niobium, put the aluminum wires in them with the right composition, and I would put that inside a copper nickel tube, and I would swage it down. A swaging machine is just these big rotary hammers. And so if I want to taper down a wire or a rod, I just stick it in this machine, which basically has these hammers going around in circles, and they pound it. They're basically cold forging it like that. So I had several little swaging machines, and I would swage it from 3/4 of an inch or 1/2 inch down to 1/8 of an inch. And then I would throw the whole thing in nitric acid inside a hood. And then I get fuming nitric, and if I wanted to get high or something, you just have this orange smoke pouring off. And you ate away the copper nickel, but you wouldn't eat away the niobium, because niobium and tantalum have tremendous corrosion resistance. They're not touched by nitric acid at all, neither is aluminum particularly. So then I take those wires and I would bundle them up again, either 19 or what is it, 261. Anyway, there are different numbers of, if you have a hexagonal array in circles, 7 is the first one in the center with 6 around it, and then if you have another row, it's 19, and the next is 30, whatever it is. Anyway, there's a series. So I'd bundle those and I'd swage those. Eventually, I'd get the thing down where I had enough deformation by cold welding. I had cold welded this together, and I could start wire drawing it. And I eventually ended up with 10,000ths of an inch, 1/4 millimeter diameter wires that had 100,000 fibers of aluminum in them. And I could take those and I could just resistively heat them. Basically, I had a vacuum chamber and just a big light bulb, and turn the electric current on, and you see the thing react, and I'd make my intermetallic compound, which was the superconductor. I also had to, at one time, heat treat these things at 1700 degrees centigrade. And so in terms of furnaces, I said you typically use a molybdenum furnace. Well, I designed a tantalum furnace and built it and machined it and everything. It worked great. I could turn that thing on like a light bulb and heat up. But back in those days, my thesis advisor thought I needed to learn electronics, so he was going to make me build my own controller. Okay, you could buy one for $1,000. And I'm not an electrical engineer, but he decided I should design my own. So I decided I was not going to design my own. So I went out and I bought platinum rhodium wire, and I wound my own furnace out of platinum rhodium wire. In platinum rhodium wire, I could go to 1600 C, but you're so close to the melting point of like 1800 C, you'd actually get crystallization or vaporization of the platinum, and I'd form these little platinum crystals, but that's because the wire's falling apart, and I get like 10 hours out of the furnace before I'd have to wrap another platinum rhodium wire. When I was all done, the technician's drawer had probably $20,000 worth of platinum, used platinum furnaces in it when it was all done, because my thesis advisor wouldn't buy me a $1,000 platinum controller, or not platinum controller, but furnace controller. So there's always a way around things, right? He never realized it cost him 20 times as much. Any other questions about random things? Told you, when I ask questions, I give you an answer. Okay, see you tomorrow. Tomorrow we'll finish up forging and rolling.